Welcome back to NPTEL live session for week 7. We'll be shortly starting our session. Thank you for joining.
Yes, ma'am.
For other people to join, we can have a recap for what we have left the last session with. We were talking about C7H7 complexes. Basically, the preparation we started with. I hope my voice is clear. If not, please let me know. So this can be prepared by various methods. One of such methods that we have seen was sigma pi rearrangement. Time system. We have and there is a substitution of COCl. Now in presence of the radium carbon complex, we leave out Cl and coordinate with your carbon. Just can you hear me now?
Yes, ma'am. But it's quite low. If you just increase your voice, that would be fine, ma'am.
Okay. Okay, so I was talking about that how we can prepare C7H7 complexes. And here we have seen like if you are taking a substituted triene system and when we are treating it with rhenium complex, the chlorine is going out and then rhenium is going to coordinate with your carbonyl. Now, what we can expect over here, this we have already seen in last session. I'm just giving a recap of it before we move on to the reactivity session. So now what we can expect over here, the carbonyl group will coordinate with your rhenium as it was having a negative charge, and the other CO5 can be as such. Now, when we are giving a presence of light, one of the carbonyl group will go out, and ultimately it would form a system like where we have proton and rhenium CO whole 5. Moving ahead, when it is being treated with Me3NO, it would try to complete the coordination number around your rhenium center. So when we have system like this way, so it is going to take up 3 centers, 1, 2, and 3. So we can make it like this way. Could coordinate with your rhenium to fulfill its valence electrons. And ultimately, again in presence of Me3NO, it is going to take now 5 centers in picture. So it is nothing but the rearrangement of your sigma and pi bonds, where earlier it is only bonding with the sigma. Here it is making a sigma bond. Then pi electrons are also in contact with the rhenium. There means sigma pi rearrangement is happening. Earlier only one bond was there. Then we included one pi bond. Now we are going to include 2 pi bonds. And based on that, another carbonyl will leave the coordination sphere. So here, now we are going to include 1, 2, 3, 4, and 5 centers. So this half semicircle is going to depict that which are the centers which are going to participate in coordinating with your rhenium, forming CO3, keeping the valence electron count as same. So this is it. Here we saw that this is also a C7H7 system, but it is having a sigma arrangement, sigma bonding, we can say. But here both sigma and pi arrangements, pi bonding is happening. Here it was hapticity 3, now it is hapticity 5, and it was hapticity 1. So this is where we can make a transition metal complex with C7H7 ligand going from sigma bonding to the pi arrangements. So this was one of such methods, and that we ended up having a discussion in the last session. Now, today we are going to talk about the transition metal complexes with C7H7 ligand. Majorly, it's reactivity. So we are going to talk about its reactivity of the transition metal complexes with C7H7 ligand. So basically, we are going to talk about first thing is metallation. So how it undergoes a metallation process. For example, I have a complex where M is a metal center, and it is coordinated with a C5H5 ligand, which is a cyclopentadienyl ligand, which we have already studied in our previous sessions. And other side, it is having a C7H7 ligand, this one. So it is having a coordination with CP and C7H7. Now, in presence of lithium, it will undergo a lithiation process. As I mentioned, we were talking about metallation, which is first example that we are taking is lithiation. So in presence of lithium, there is a possibility that one of the bonds of C5H5 is getting lithiated, or it can be the lithiation can happen on the C7H7 side also. So one product that we can expect of the lithium is coming over here. If your metal center is vanadium or chromium, if your metal center is titanium or chromium, in chromium there are two possibilities that you can have a metallation happening on either side. So we can expect the metallation is happening at this side. So this is a process of lithiation, and this is a property of your C7H7 ligand. Already in C5H5 ligand, we have seen this kind of nature. The similar kind of nature we saw in C7H7 as well. Now moving ahead to look into the reactivity of it. So if we have titanium and a CP group at top, and on the other side we have a C7H7 ligand. Firstly, we are treating it with N-butyl lithium, which is a source of lithium. As I mentioned that we are going to first do the lithiation, and then we will be talking about how another ligand can come into picture. And in the second step, we are giving a source of phosphine group. So how is it going to take up? And also in presence of Tomeda, which is nothing but a strong base, which is tetramethyl ethylene diamine, to abstract your proton, and that proton can bind with your butyl group, releasing the butane gas. If you can understand it well, if I'm taking a CP group and if it is having an H bond over here, if you're giving a source of nitrogen with lone pair, which is a part of Tomeda, it will attack onto this one and would create, this would go as a H nature, as a H positive, and this can be taken up by the butyl group and therefore making a butane gas release. Ultimately, it would create a minus charge onto your ring, making a CP like this way. This can further attack onto your lithium positive. So once lithiation happens, we end up getting, we can expect getting, in this particular case, in case of this one, because we are using a very strong base, there is a possibility of deprotonating both sides. So we can have a lithium over here as well and here as well. Earlier in other cases, when we were not using any base, we were expecting that in presence of, if metal is titanium, we can either have, if we have a metal, vanadium or chromium, we can have lithium over here or lithium at this side. If we have a titanium, lithiation was predominantly happening on the C7H7, but in presence of a Tomeda, which is a strong base that can deprotonate from both the ligands, and therefore we can expect to have a lithiation on both sides. If there is any question so far, please let me know. Now when
No, ma'am, it's clear.
Okay. Now the voice is clear.
Yes, ma'am.
So the second step then we are having when we are treating with a phosphine group where we have an R2 phosphorus and chlorine. And here you can clearly see that two molecules of this one can release two molecules of lithium chloride, and in place of lithium, it is going to be bind with your phosphorus group. And ultimately, because this is positive, this is negative, and ultimately you will be ending up having this is the same group. In place of lithium, now you are having another group, which is PR2, which is nothing but your phosphine group. So this has been given by Roche in 1991. So this is a part of the reactivity of C7H7 ligand. Already the C5H5 ligand reactivity we have seen in full description in earlier lectures. But here we are focusing on the C7H7 system. So we have seen that in presence of a strong base, there would be possibility of having a lithiation on both ends. And once the lithiation is there, and you can see that how it can be removed by giving a chlorine source, another electrophile can come and attack onto your CP and C7H7. Now, in the similar scenario, if I'm not giving a very strong base, which is Tomeda, so what will happen? If I'm taking just the C5H5 titanium and bind with C7H7, now I'm only giving N-butyl lithium without any base. And in the second step, I'm having Pr2Cl. And we know that if there is no base, titanium in presence of the metal center as titanium, it would predominantly would attack onto, would do the lithiation on the C7H7, meaning we will first get this product having a lithiation over here and leaving out a butane gas. And ultimately, when it is being treated with Pr2Cl, in place of the lithium, it would give you a product like this one. So it is the nature of the metal that it creates a reactivity, and predominantly C7H7 is coming into picture and lithiation is happening on that. So you can see the clear difference in presence of base and in absence of base, how your product formation differs, right? So this is also been given by Roche in 1991. Now moving ahead to the next example or the reactivity part. Now we are taking a case of vanadium. You need to remember, like, we have taken the lithiation thing at first, and lithiation step is very, very important. In case of vanadium, it happens at C5H5. In chromium, it can happen at both places. And in titanium, it happened at C7H7. So we have considered the example of titanium. Now we are taking an example with similar ligands with vanadium. So we have a C5H5 system with vanadium. And on the other side, you have C7H7. Now I'm first giving a source of lithium, n-butyl lithium I'm giving. And in the second step, I'm giving a source of iodine, which would be I positive over here, in a diethyl ether medium. So what we can expect, where the lithiation is going to happen and where the iodine will go at the end. So we very well know that we have a vanadium, and vanadium does the lithiation at the C5H5 in comparison to or relative to C7H7. So we can expect to have the product after lithiation. We can expect it to have iodine coming at the center. If that is a scenario and we have an aryl iodide over here, we have a C5H5 and iodine group over here. Now it can further react if we are giving a source of Me3 tin having a alkyne group and Me3 over here in presence of the catalyst, which is PPH3. Just a second. Okay, so PPH3 twice palladium Cl2. So it's a square planar complex of palladium with 2 Cl and 2 PPH3. In presence of this catalyst, and when we are having an alkyne group, it means it wants to undergo a coupling reaction between this aryl group and these centers, these alkynes and this aryl group. So for this particular system, we need to have two molecules of this one, because here we are having an alkyne and it needs to make a bond between the two rings. Ultimately, we will end up having two molecules of vanadium bound with C5H5 and C7H7. And this bond is going to make a triple bond between there are two carbons. And then we are having in another ring, another group. And ultimately, it would end up making a coupled product. This is called a coupling reaction, as we are using a palladium-based metal system. And this has been given in 2004 by Elshin Broish. You don't have to remember the name, but it is always good that if you know that who has invented or discovered the particular reaction. So this is our major portion of reactivity, was to have lithiation at what step. So we got to know that lithiation is going to happen at this C5H5. Once the lithiation was done and we have an aryl iodide system over here, once we have made this is having a tremendous number of applications. One such application is your coupling reaction, when you need to react your aryl iodide with certain alkyne system, and you are coupling the two molecules having an alkyne group in between. So where palladium catalyst plays an important role. This could have also happened at this particular position, but since we are using a vanadium, this has gone to a C5H5. So yeah, this was about the reactivity of C7H7. Next part of its reactivity is when we have a C7H7 ligand and it is having a molybdenum with 3 carbonyl groups and with a positive sign. Now, since we are having a positive sign, that means this charge is on molybdenum, and we are treating it with a nucleophile CH3O. This is a methoxide group. This is a nucleophile. Since your metal center is having a positive, there is a possibility of attacking the methoxide directly onto the molybdenum, but it actually attacks onto your C7H7. So this positive charge being accumulated towards a C7H7 group. So what we can expect over here, this can work as a benzene group, and the 7 center goes above, and this takes up your OCH3 and H, and these all 6 will coordinate with molybdenum, carbonyl, carbonyl, and carbonyl. So this is where the addition of nucleophile happens onto your C7H7 ligand. So there is no substitution, there is no elimination, it's just the addition onto your C7H7 center and making a OCH3 bond with your carbon center of the C7H7. So the topic was here the addition of nucleophile. So these are the examples of how your C7H7 system reacts. Moving towards the next example, which is the change in hapticity. You might be aware of what is hapticity, what does hapticity means. So if I'm taking an example of molybdenum again with 3 carbonyls and 2 carbonyls and 1 Cl, and another group we are having is C7H7 with 1, 2, 1 and 2. We are making a substitution over here. Okay, so then alternatively over here and then over here. So in this particular case, when we are taking a ring over the system, it's in eta 7. That means 7 centers are involved. So if you will actually calculate the number of valence electrons, so if this eta 7 hapticity is there, so that means it is involved in 7 electrons. Molybdenum belongs to chromium group, which would give you a 6 electrons. One carbonyl gives you 2 electrons, another will give you 2, and one chlorine will give you 1 electron, total 5 electrons. So if you calculate, it is 18 valence electron system. So maintaining the 18 valence electron system, how it can undergo the change in hapticity, we will just look now. So now we are using a DMPE. DMPE is nothing but a substituted phosphine group having an ethane molecule. That means dimethyl, bis dimethyl phosphinoethane, where we have a group which is having a 2 carbon molecule centers, and here there are methyl groups, and this is your DMPE. Now, when this is 2 and 2, 4 electron centers, it is bound to change the hapticity. Either it can remove your carbonyl group, but you're not providing any source. And compared to the carbonyl, the change in hapticity is more labile. So whenever you are having a chance of whether you can dissociate any of the ligands or you can change the hapticity, hapticity would be the one such factor which would happen at a faster rate. So when I'm going to introduce a ligand which is having 4 electrons, so it needs to maintain the 18 valence electron as well. So if I'm giving 4 electrons, it needs to remove certain 4 electrons from the original system. So where it goes? So actually it would go from eta 7 to eta 3 and therefore maintaining the 18 valence electrons. So what we can expect over here, here we have a molybdenum, we have a Cl, CO, these all 3 ligands would remain as such. Now I'm having a phosphorus bond. And at the top, we can have again the C7H7. But since we said that it is not a eta 7 anymore, so only 3 centers would be involved. So we can take 1, 2, and 3, these 3 centers, and the other 2 bonds remain as such. So only 3 centers, eta 3 is there. Now if you'll calculate here, 3 electrons are coming from your C7H7 because of eta 3 hapticity. 5 are coming from 2 carbonyl and 1 chloro. Molybdenum is giving you 6 electrons and 2 phosphorus are giving you 4 electrons. Therefore, it's an 18 valence electron. So this is how the reactivity plays a very important role. So you need to make a judgment when you have an option whether you can remove the ligands, because in many of the cases you might have seen to maintain the hapticity or to involve any other ligand, you lose the CO and you introduce the phosphorus group. But here when you have a chance of going from eta 7 to eta 3, eta 4, it would prefer to have this kind of change in hapticity. Now, once we have made this eta 3 system, and which means molybdenum, Cl, CO, CO, phosphorus, and here we have these 3 centers and it remains as it is. Now, when I'm giving a source of light, what would really happen? Now, in presence of light, it is very easy to cleave your CO either in thermal energy or in photo light. So you're releasing 2 molecules of carbonyl group, that means CO gas, and therefore 4 electrons are gone. Now it again has to go, it has to accommodate 4 more electrons and we are not providing any other ligand. So the rearrangement of eta 3 to eta 7 hapticity would happen and ultimately it would be in a stable form where hapticity of 7 is there with the C7H7 ligand. So it is again, so it started with eta 7, then it went to eta 3 and ultimately it went to eta 7 in presence of the conditions that we have provided, and it makes again an 18 valence electron. So if there is any doubt, please let me know before we move ahead. So this has been given by Green in 1993.
No doubts, ma'am.
So basically, there was a substitution of carbonyl group in presence of light. And if we ultimately see the reaction, that phosphorus groups have substituted your carbonyl, but the conditions have to be very, very clear. And you need to depict, okay, whether the hapticity is changing or whether that the first step itself, carbonyl is going out. So another example that we can take for this particular system, where we are changing the total valence electrons, making from 16 to 18 valence. So we have here a C7H7 system and a zirconium connected with a fused C5H5 or an indole kind of system. So when you're giving a source of PME3, so this is basically a 16 valence electron. Because it is going to give you, okay, one announcement that this meeting will be ending up in next 10 minutes. Please rejoin the same link. So this is 7 electrons. Zirconium will give you 4, that's 11. And 5 is coming from your C5H5. Basically, it becomes a 16 valence electrons. And in presence of vacuum and heating and PME3, what would happen? It undergoes nothing but an attack of the PME3 onto the zirconium center and making it a, I'm just writing a CP and the fused ring you can just see over here. So here it is 7 electrons, here it is 5, here it's 4, and 2 is coming from here. Total 18 valence electrons. So change from 16 to 18 valence electrons and stability is being attained. So this has also been given by Green in 1992. Moving ahead, we have another example for this reactivity. So these are all different examples, and but you have to understand and you need to know like where in presence of nucleophile the attack is going to happen, where the rearrangement sigma and pi bonds are going to happen, where the hapticity is going to change, and where we can expect the stability of the complex by attaining an 18 valence electron configuration. So now we have another example of ligand bridged dinuclear complex. So firstly, we are taking an iron-based system which is connected, coordinated with 3 carbonyl groups, and we have C7H7 where 3 centers are there. So we can expect this one. And the other 2 bonds are as it is. And now when it is being treated with a complex which is rhodium and a dimer, when it is being treated with this one, we have a negative charge and we have a ligand which is having only eta 3 has been used. Not all the coordination has been used from the C7H7. So it tries to complete the coordination by getting involved in the metallation with other metal center. So what I'm trying to say is, so here it would be having C7H7 in the middle. So 3 carbons would be binding with your iron and other 4 would be binding with your rhodium. Since it is having a negative charge, it would fill up the valency by making a bond with rhodium, and other ligands remain as it is, Cu and Co. Here was one CO and here was one CO. This chlorine, which was giving a charge onto this rhodium, that has been removed. That's why it was able to form a binding with a bond with the iron as well as the C7H7. So here, what we want to try to say is partial coordination, which we were seeing in this particular substrate. Partial coordination, this is an important point. Coordination of C7H7 has led to the metal-metal bond formation, where one metal center is iron and another is rhodium. Bond formation through ligand bridging. So this particular ligand has gone into the bridging, and one center it has one bond it has made with the iron, other bonding it has done with the rhodium, making a very stable complex and giving a metal-metal bond. So this was all about the C7H7 ligand, and since we are going to start again for C8H8 ligand, I would end up this meeting. Please rejoin the same meeting.